So in this episode, after us performing the docking, as I showed you, we can use a SimDock, or we can use SwissDock, or we can use the locally installed the Vina tool, the Autodock tools. And in the locally installed Autodock tools, I think I will also do a video on that. It's just it's easy. It's the same as these online servers. Though for it gives you a feel of how docking really takes place and your manual control over everything. But accuracy is actually comparable to all the web servers. Though it takes more time of preparing the configurations and all that stuff. So if we have obtained the dockings, we can import our file. Let me import here. Open, and this is the docking that I did in the last video, where I used SwissDock, and I can use this VinaDock. I can first put in this, and you can see SwissDock gave us two poses, though it gives more, but it's okay. I can use these two. You can see these are the poses. Then we can also import the PDBQT. Now make sure you import the PDBQT, which is the system, not the PDB. Well, this folder is what I showed you, what we obtained after downloading the docking results from the SwissDock. So I import the system, and well, it looks like this. So we are going to study and take note of what information can we get from this. So one of the information that we can get from this is that is the arrangement of this protein. Just looking at it, you can see that the alpha helix, these ones that are spiral, are arranged in a smart way, and then there forms a barrel like of the beta sheets. Well, this can be confusing to someone if he's not well conversant with the structures of proteins. But let me start with a simpler one. What we can do. The other thing that I can see is that this can be the base of the enzyme, and then from this side can be the access point of the substrate. And as I told you, that I see alpha helixes surrounding the cavity, the opening of the cavity, and on this I see that all these alpha helixes are joined, some to beta sheets, by flexible loops. You can see this is a flexible loop joining this to this, and this is another flexible loop, this one joining this helix to this sheet. This is another flexible loop joining this helix to this. So it forms a repeated pattern that can give us some good information. Let me see if I can get another flexible loop. There is another flexible loop from this one going all the way to the end of this one. Okay, so ideally you can see it here, that on the surface there could be the alpha helix that are joined to the beta sheets with via flexible loops. Yeah, That is ideally what we can get here, and this is some good information. Yeah, you can see it here. Another good information is that okay, another good, yeah, you can also see this one going all the way to the sheet down here. Okay, so another good information that we can get is that we need to understand what is the importance of these flexible loops in such a structure. We know that alpha helix and the beta sheets are so flexible, are so stable because they are secondary structures. And then another thing is the loops. These loops should play a role because we see a repeated pattern, and when you can see the pattern being repeated, and one of the functions of these loops is that they vibrate a lot on small kinetic energy. You know, when we put like heat energy, maybe a 30-degree temperature, these loops can vibrate a lot, and the pattern of vibration determines specificity. You understand? And then before you start to understand the working and the structure of the enzyme, you need to understand if the enzyme is specific, or if the enzyme has like single substrate specificity or broad specificity. Now for this D-Hydantoinase, it has broad substrate specificity, and we could tell that while these structures are stable, like the helix and the sheet maintaining a 3D dimension structure, a particular structure of the enzyme, these loops can play a role in regulating the specificity, or in making the enzyme have a broader specificity. Of interest is that take an example. If we get tryptophan somewhere here, and we replace it with alanine, you know, the specificity will not be the same. You understand? So however, it can, if we have if a substrate prefers alanine, and then this enzyme, and then another substrate prefers serine, you know, both of the enzymes having serine and alanine might work, because the level of vibration of serine and alanine might be the same. But if there is tryptophan, the level of vibration is totally different, and these heavy and bulky amino acid residues confer single substrate specificity, while the smaller ones present in these loops confer broad specificity. So this is one of the quick information that we can get from this structure. And what we can do next is we can try to understand more about the binding cavity, and how and which side binds. Okay, so ideally the side where the reaction takes place is the hydantoinase side, the hydrazine. Is it a hydrazine ring? Okay, this ring, yes, it's where the reaction takes place. So obviously it should be positioned first to the active site. So if you don't understand how where the reaction takes place, you could be confused by this pose, because this pose has the hydroxyl ring, the hydroxy group facing the active site, which is not the case with this one. So what we can do next is before for good representation, to move this structure you press Ctrl and right click. You can move the structure around. And for good representation and taking report, before we go in deeper, we can try to see how we navigate around PyMOL. What we can do is we go to first to display, and we go to background and we choose white. So this is good for paper representation. And again, we can go, because this doesn't give us any information, but good information is from